Hello everyone, my name is Tulipa, and in this tutorial Grant and I will talk about the fundamentals of IPT. After introducing our university, we will briefly look at the history and the current status of wireless power transfer technology in order to discuss how this technology evolved over the last 100 plus years. Then we will look at the fundamentals of IPT technology to understand what aspects of a wireless charging system can be improved to make them more widely used in the future. After this, Grant will talk about magnetic designs used in IPT systems. We are from the University of Auckland, the most prestigious university in New Zealand. It is also ranked among the top 100 universities in the world. We have about 5,000 staff members and about 40,000 students at the University of Auckland. Out of the 9 faculties, we come from the Faculty of Engineering. Within the Faculty of Engineering, there are 5 departments, and we are from the Department of Electrical, Computer and Software Engineering. We are one of the biggest departments with over 150 postgraduates and 750 undergraduate students. This is our new engineering building with state-of-the-art research and teaching laboratories. Grant, myself, Patrick and Udaya lead the Power Electronic Research Group at the University of Auckland. Our research group is very well known worldwide for the pioneering work we have done in the field of inductive power transfer. This work started in the 80s by Professor John Boyce, and since then his students Grant, Patrick and Udaya has been quite active in this area. We collaborate with many leading universities around the world. Also, IP generated by our team is licensed to companies around the world, generating millions of dollars of research funding. Among us, we have about 35 postgraduate students and 10 research fellows. Let's look at the history of wireless power transfer technology. Wireless power transfer can be broadly divided into 2 categories as radiative and non-radiative near-field power transfer. Radiative power transfer systems mainly use microwaves, optical beams, or ultrasonic waves to transfer power over a larger distance. However, the efficiency of these systems tend to be so far poor, and as such, they are mainly at an experimental stage. Airfield Alliance is developing standards for these systems to address safety, interoperability, and functionality expectations. In the picture, you can see 2 experiments conducted to test long-distance power transfer. One was done almost 50 years ago by NASA. The other more recent one, conducted by Mitsubishi, still has some of the fundamental limitations found in these earlier experiments. Inductive and capacitive power transfer is used to deliver power over a small distance using near-field coupling. Capacitive power transfer, however, is still not mature and has some fundamental limitations when it comes to transferring kilowatts of power. Therefore, resonant IPT technology is regarded as the most suitable to use in wireless EV charging. Often, IPT systems are also referred to as highly resonant systems or resonance coupling. Standard bodies such as WPTC, SAE have developed standards to ensure safety, interoperability, and functionality of IPT-based wireless power transfer systems. Inductive power transfer started with the work done by Tesla, Houghton, and LeBlanc in the late 19th century. After this, in the 60s, Schroeder did quite a bit of work to develop high-frequency resonant IPT systems for biomedical applications. The concepts that were developed at this time are used even in modern-day IPT systems. For example, circular coils as you can see here in the picture. In the 70s, one of the staff members from our university, Professor Otto, started looking at IPT for EV charging. In parallel, similar work was done in the US. However, one of the most important developments took place when Professor John Boyce and his team from our group started developing industrial systems for Daifuku, Wampler, back in the 90s. This partnership with the industry helped us show the benefits of using inductive power transfer technology in real-world applications. Since the 90s, there has been many developments in this field. By about 2010, many companies and research groups worldwide started working in this area, developing IPT solutions for many applications. As you can see in this timeline, our group has been quite lucky to work closely with industry, developing solutions and helping widespread adaptation of this technology. Currently, we have technologies that enable us to develop IPT-based wireless power transfer systems with power ratings as high as a few hundred kilowatts. This is helped by the advances in magnetic designs and power electronics that allow not only unidirectional power flow but also bidirectional power flow. These systems can be designed to achieve efficiencies as high as 97%. Power transfer distance range from a few millimeters to about half a meter. Here in the picture, however, an IPT system is designed to transfer power across a room using rather large transmitter coils. Since the early 90s, IPT technology has been used in many sectors. First applications of IPT has been in factory automation and materials handling. Then it was developed to charge consumer electronics and EVs. IPT is also used for lighting applications, especially in tunnel lighting. It is also used to power biomedical implants and industrial machinery as well as robots. Now let's see how an IPT system works so we can understand what aspects may be improved in the future. An IPT system can be divided into two separate subsystems as the primary and the secondary. The secondary is also sometimes referred to as the pickup. The primary consists of a transmitter coil which is compensated using a resonant network. A power electronics converter is employed to drive the primary coil through a compensation network to generate a high frequency current in it. This current creates a high frequency magnetic field in the vicinity of the primary coil. On the secondary, there is a receiver coil that intercepts this magnetic field, and as a result, a voltage is induced across it. A compensation network with a power electronics converter is used to convert this voltage to a form useful to power or charge the load. The behavior of the primary and the secondary coils is very important to the functionality of an IPT system. We can think of these two coils as a very loosely coupled transformer. So the behavior of these two coils can be modeled using the traditional transformer model as shown in this diagram. The coupling factor K between the two coils in an IPT system is typically lower than 40%. This leads to a rather large leakage inductance since the mutual inductance is proportional to the coupling factor K. When it comes to studying and designing IPT systems, we hardly use the transformer model. Instead, we use the mutual inductor model where we describe the magnetic coupling between the two coils using an induced voltage source that is in series with each coil. This induced voltage is a function of the current in the neighboring coil as shown in this slide. Using this mutual inductor model, we can derive a very basic equation to describe the power flow from the primary to the secondary. This is done by expressing the uncompensated VA capacity, or the SU of a secondary coil. SU of the secondary coil is equal to the product between the induced voltage across it and the current that would flow through this coil if it's been short-circuited. We can extend this analysis to derive a comprehensive expression that tells how much power we can transfer through an IPT system in terms of the VA in each the primary and the secondary coils. We can see from this analysis here that the power we are able to transfer is simply K, or the coupling factor, times the square root of the VA product. This fundamental relationship holds regardless of the improvements we make to the power electronics or the compensation networks. The main motive of these improvements to the power electronics and compensation techniques are to ensure the sin theta term in this equation is kept approximately at about 1 over a wide range of operating conditions. With regard to the coil design, our target should be to make sure K is kept relatively constant at a reasonable value over a wide range of operating conditions. The most lossy component in an IPT system are the primary and secondary coils. This is due to core and copper losses in them. We can bundle these losses together and express them as a quality factor Q of each coil. Using the Q of each coil, we can derive the best case efficiency achievable and show that this is achieved when the VAs in the two coils are distributed based on their quality factors. As an example, consider an IPT system where the coupling factor can range between 0.01 and 0.03 due to changes in power transmission distance. If both the primary and the secondary coils have a Q of 400, then as we can see from these tables, regardless of the coupling factor, maximum efficiency is observed when the VAs are distributed equally. Of course, the efficiency drops significantly with decreasing coupling factor, as we need to have more VAs in the two coils. Because the coupling factor between the primary and the secondary coils is quite low, to improve the power transfer capability, we need to employ compensation networks that are tuned to resonate at the operating frequency. Let's look at how these compensation networks work. For example, if we had not used a compensation network, the amount of power that can be extracted by a resistive load connected across the secondary can be derived easily using circuit analysis techniques. From this analysis, we can immediately see that the inductance of the secondary coil limit the ability to supply current to the resistive load. As the current to the load is limited, it also limits the power delivered to the load. There is a maximum amount of power that can be delivered, and this happens with the load resistance when the load resistance is equal to the reactance of the secondary coil. In this example, we can see that there needs to be 1 VA in the primary coil in order to deliver 5 millivolts to the load if the coupling factor is 10%. So to deliver tens of watts, we need to have thousands of VAs in the coil, leading to extremely poor efficiency. To improve the power transfer and the efficiency, we need to somehow cancel the reactance of the secondary coil and make the secondary coil look like an ideal voltage source or an ideal current source. This can be achieved using resonance, a technique that was discovered by Hertz in the 1880s. Similar to the inductance of the secondary coil, the inductance of the primary coil limits the ability of the primary power electronics converter to deliver power. This is because the impedance seen by the primary power electronics converter has a significantly large reactive component introduced by the inductance of the primary coil. Because of the reactance of the primary coil, the primary power electronics converter needs to supply large amounts of VAs to transfer a small fraction of that as real power. Again, we can use resonance to negate the reactance of the primary coil and therefore to improve the power transfer. There are many resonant compensation network types used in IPT systems. The most popular are the series and parallel compensation networks. However, parallel resonance is not the preferred choice on the primary anymore, as most modern systems use voltage source power electronic converters on the primary. LCL type compensation is often employed in the primary as it can be derived easily by a voltage source power converter. Alternatively, series compensation can be used in the primary. More advanced types of compensation networks, including hybrid compensation and impedance compression networks, have also been proposed. When it comes to EV charging, it is advantageous to choose the compensation networks such that it makes the secondary behaves as a current source, helping us charge the battery. This slide summarizes the properties of 5 different types of IPT systems categorized based on the type of compensation networks employed on the primary and on the secondary. Now that we know how compensation networks work, let's look at what type of power converters are commonly used in IPT systems. As discussed earlier, voltage source converters are commonly used in modern-day IPT primaries. The most common is to use a full bridge converter to drive an LCL or series compensated primary coil. Alternatively, half bridges can be used in low power applications. Since the fundamental generated by the primary converter needs to be in the order of tens of kilohertz, we cannot use standard PWM techniques to control the primary converter. Instead, we commonly use voltage cancellation techniques with converters such as full bridge converters. We can implement voltage cancellation control using phase shift modulation. Though there are other ways to do this, phase shift modulation is the most common. Here, each half bridge of the converter is operated at a 50% duty cycle. The phase shift between the two legs is controlled to regulate the RMS value of the fundamental component. To explore this further, we can derive a mathematical expression for the output voltage generated by a full bridge converter using Fourier series. Here we can see that the output of the full bridge converter has odd harmonics. Magnitudes of both the fundamental and the harmonics are a function of the phase shift modulation. Since IPT systems are higher order resonance circuits, we can simply only consider the fundamental component to understand the behavior of an IPT system. Depending on how the resonance circuits are tuned, the impedance seen by the full bridge converter can be either capacitive or inductive. If this impedance is capacitive, we have hard switching leading to significantly higher losses in the converter. Therefore, in many cases, we try to tune the resonance circuits so that the impedance seen by the converter is inductive under all operating conditions. However, this leads to extra conduction losses due to circulating currents. Inductive loading helps the inverter to soft switch and therefore reduce the switching losses significantly. Instead of tuning the resonant network to reflect an inductive load across the converter, we can also use new and improved converter topologies. In the early days, we used current source resonant converters to drive the primary coil of an IPT system. This is not so much popular these days in high power systems, as the current sourced resonant converters tend to be sensitive to operating conditions. However, there are new and improved topologies that address some of these shortcomings. In the secondary side, usually we use a standard diode rectifier or a current double rectifier to derive a DC output. This is usually followed by a DC to DC converter to derive a regulated output. One of the most widely used DC to DC converter topologies in the secondary is the short circuit controller. This was originally proposed by one of our colleagues, Professor John Boyce, in the early 90s. It is also called a decoupling controller, as turning on the switch in this converter short circuits the resonant tank and decouples the secondary from the primary. At the University of Auckland, we also pioneered the work that helped IPT systems transfer bidirectional power. To achieve this, we introduced the use of an active secondary converter that is synchronized with the primary power electronics converter. By changing the operating angle of the active secondary with respect to the primary converter, we can easily switch the direction of power flow. This type of systems help realize vehicle-to-grid services, as an example. Having an active secondary converter also provide a number of additional advantages which are currently investigated by our group. One of these features we exploited is the ability to use the relative phase between the two converters to compensate for changes in coupling factor and in coil inductance introduced by misalignment. This work helps derive the optimum control conditions to improve efficiency of an IPT system when there is misalignment between the coils. This is the end of my part of the presentation, and I hoped it helped you learn how an IPT system works. If you'd like to learn more about IPT technology, you can visit my website referenced here. Grant will now talk about the magnetics.
Good day, everyone. My name is Professor Grant Kovac. I'm going to follow on from Dileepa in this fundamentals tutorial and talk a little bit about the magnetic options which we have developed here, in particular for electric vehicle charging systems. The overview of my system is shown here. I'm going to start with single coil options. The most common of these are single-sided, either non-polarized or polarized. Of these, we're going to start with the circular non-polarized. So this can either be a circular, square, or rectangular coil on a ferrite backplate or radial spokes of ferrite. The field is launched from one side of the ferrite and retrieved on the other side. And good coupling is normally achieved at about a height of 1/4 of the diameter of the pad. To stop field penetrating the vehicle, we place an aluminium shield. Now we're also interested in the field which is present outside the pad or outside this aluminium. If this is problematic and it's in an area of concern, then we can add a lip to the aluminium, and you can see that this will reduce further the leakage out the side of the pad. And that's important for IC and IP regulations in electric vehicle charging. When the secondary is placed directly at the center of the primary pad at an appropriate height, we will get the highest volt amps into it. As it moves laterally, you can see that the volt amps that are coupled into this secondary drop away. And for a 500 millimeter diameter coil, when we reach 250 millimeters, we expect that we will get zero coupling into that primary, from the primary into the secondary. And that's because the field entering the secondary and exiting the secondary sums to 0 within the coil on the secondary. This means that the circular pad is ideal for stationary applications, but it's more challenging for dynamic because we'll actually hit field nulls before we get to the next pad in line. For applications where we want to move this into a roadway system, we may not want ferrite to be present at all. In that case, here's an example of a circular coil system with no ferrite. But what has been added is an anti-wound coil or a reflection coil with 1/3 the turns at some distance below it. This has been added to stop the field penetrating further into a roadway environment. And if you make this reflection coil 30% larger, you can actually control the field leakage out the side. And so the power to leakage becomes very similar to a ferrite-based system. However, you've got coupling factors which are only around about 2/3, and therefore the volt amps required by this system is normally 2 to 2.5 times larger than a ferrite-based system. The second most common single-sided topology is called the polarized double D. Here you can see that it's constructed with a figure 8 wound coil as a single system and a back plate of either strips of ferrite or it could be a ferrite sheet. The field launches from the center of this part of the figure 8 vertically, becomes horizontal at the center of the pad, and then enters the ferrite again and then returns back through the ferrite. This reduced ferrite material causes us to have a lower inductance and is significant in that we don't have to have such a large body of ferrite. We can spread the center winding, and this pushes out the actual launching of the main field from either side and the collection. And that enables us to get a much higher field pitch than we can from a circular coil, typically 1.5 to 2 times larger, so that we can either capture more field or have a wider tolerance. The downside of the double D is we also get a weak flux linkage around the end portions. And this means that while it has wider tolerance and a higher field capture than a given circular system, it will produce slightly larger field leakage. Overall, both the circular and the double D are excellent topologies for creating wireless charging electric vehicle systems. They have high native quality factors, which means low loss. Ferriteless double D primary systems can also be created in the same way that they can be for the circular. In these cases, we also add a reflection coil to stop the field going into the ground, and that would also best be designed with 1/3 the turns ratio and being 30% larger. When we make a comparison of a ferrite primary, here the primary is shown in the photo to be above the secondary, but it's reversed in the field plot below. We can see that the typical leakages at a particular point or points at distances around that particular system. When we look at that in comparison to a ferriteless system, we can see that we can have much lower leakages. However, we need to actually drive the ferriteless system with more than 2.5 times the VA because the coupling factors are typically 2/3. We can improve the coupling factor by adding a small amount of ferrite back into the actual system. So it's like a hybrid between a ferriteless and a full ferrite system. And that enables us to lower the volt amp requirement and also improve the leakage again. And this is obviously a research point of where do you place the ferrite and how can you best design your system. But we can have much lower leakages than a ferrite system. and make it more robust. Comparing the two systems, we can actually design a system which is circular and a system which is a double D using the same pad areas, same inductances, drive them with the same voltamps at the same frequency, and produce the same voltamps in a secondary. Undertaking the comparisons, we can look at a 7 kilowatt zone of power transfer. And what we find is that the double D on double D produces a zone which is more than twice as large as that for a circular on circular, which indicates its capability for wider tolerance and power transfer. Interoperability is possible between double D and circular systems. However, when you place a double D secondary on a circular primary, you have to shift it so that it's sitting centered over the coil areas because it is wanting to collect the horizontal field. And if you place a circular secondary on double D primary, you shift it across to the polar areas where the field is being launched vertically. Systems which were deployed as demonstrators started in the early 90s, but the first of these that were done for light duty vehicles was showcased at EVS 24 over a gap of 220 millimeters. And this was a 2 kilowatt single phase system showing efficiencies from AC mains to battery, which were equivalent to plug-in systems of the time. So it was around 88% efficient. These have been evolved with commercial developments through Halo IPT and then Qualcomm Halo, and now with Witricity, looking at systems above 11 kilowatts and higher as we move towards the future. Over the past decade, a lot of work has been done to creating standards for wireless power transfer for light-duty vehicles. SAA J2954 details how we need to develop these systems for compliance. And just some little talk about what is now our goals. For SAA J2954 is a standard which is focused on ensuring that we have interoperability between systems which are designed. It details that there needs to be a test station used to ensure compliance. This is called Universal Ground Assembly for the primary, and the one that is used in particular is a circular, and it has a number of test vehicle assemblies which are used at various power levels. Level 1 to 3, which is typically 3.3 kVA from the mains, 7.7 kVA from the mains, up to 11.1 kVA from the mains. And it also talks about various Z classes which relate to air gaps relative to the ground, so Z1 through to Z3. The actual design systems which will come to SAE for compliance can be classified as either Class 1 or Class 2. Class 1 are considered to be the ground assemblies which are needed for public deployment, and Class 2 are the sorts of systems which were needed for either fleet or private applications, which were not going to be public. When we come to product testing, vehicle systems will be tested over their designed air gap on the actual UGA. So we are interested to ensure that they will actually comply and will be able to perform well. If a Class 2 ground assembly is provided for testing, then it will be tested up to its rating and over whatever the specified Z range is with relevant vehicle assemblies. A Class 1 ground assembly is intended for public use, needs to be tested over all power ratings within the wireless power standard over the Z ranges with all the test volt VAs. Systems are obviously tested within the region where they're expected to operate. So that means for an alignment of within plus or minus 75 millimeters in the X direction and plus or minus 100 millimeters laterally in the Y direction, allowing for roll, pitch, and yaw. Of course, these also need to take into account the battery range that might be typical on a vehicle and must comply with EMF, EMC, and also use the appropriate communication sets that are provided in J29847, and also needs to ensure that it doesn't actually cause heating for any metal objects which might be on the ground pad. System efficiency targets, AC mains to battery, are dependent on what actually we're testing. So if there's a product VA that comes out, the design has to ensure that it meets full power over at least 80% of its range and should be above 85% efficiency when it's centered at over the UGA. If a class 1 public GA has been presented, then it needs to meet minimums that are rated here. A class 2 obviously is not, it needs to be interoperable, but it has much less requirement than a public system. For those developing wireless power magnetics, you will be aware that over the last decade, global standard groups have been developing light-duty standards. The intention here is not to restrict innovation. In fact, innovation is encouraged. Any magnetic system is possible, but the key is that it must meet safety and operational compliance. For SAE, the target is to ensure it can be interoperable with other systems and complies with key operational requirements if taken into a product. SAE details the need for a test facility, its electronics, magnetics, and procedures for testing all products. If it's a product VA, then a universal ground assembly system is used to test it over its full working range. If it's a ground assembly, and it could be either a class 1 or a class 2 ground assembly, then the vehicle assemblies which are relevant over the wireless power ranges 1 to 3 and air gap ranges 1 to 3 will be used. Class 1 systems are for public use, and class 2 are used for private or fleet use. So the product testing is really dependent upon what kind of system is being tested. For class 1 GAs, it's going to be looking at testing it over all its power and Z ranges with all the relevant VAs. With class 2 GAs, then it will be only up to the rating specified for that product and over the specified working Z range. For the vehicle systems, which are the vehicle assemblies, they'll be tested on the universal ground assembly, and all of the systems will need to meet EMC, EMF, fine object detection and compliance, and need to use the appropriate communications to ensure that they talk over the relevant X, Y, Z and ranges. And the efficiency targets, which are necessary, are dependent upon whether they are a product, a class 1 public GA, or a class 2 private fleet GA. With this innovation in mind, there's been a lot of work over the last decade on multi-coil primaries. Again, the point of this is to try and increase the localized coupling, improve interoperability, but also to recognize that higher power with lower leakage is going to be needed in the future, and there's going to be needed better use of the ferrite. However, it can come with system complexity. One design that shows this off is the Multicoil Bipolar system here, with two circular coils that are essentially designed to be independent. So they can be either turned on or turned off, or operated with different currents and different phases without interacting and affecting each other. The point of this can be seen that we can shape the field so that it is underneath the secondary, And particularly when it's moved, you can see that the field may actually only need one part of the coupler to be on. As an example of this in operation, if you were to take a UGA working with a circular or a double D secondary, we can look at the field leakages and the efficiencies of this, and we find that we can actually decrease the field leakages by up to 25% if we use the multi-coil system and essentially have the same efficiencies. This can be done actually with really reduced hardware if you use one inverter and simply switch between the two coils. But as we move to higher power systems, higher complexity is required. So three-phase systems or systems that can act three-phase but also act as single-phase or two-phase systems may be required. Some examples of this are the tripolar from the University of Auckland, all the way through to Ornell's recent double D three-phase system. So in here it's using three essentially circular type coils and overlapped so that they're decoupled. And here we have three double D systems. And in between you might have a range of circular and double D systems which combined all together control the leakage while increasing power. Multi-coil vehicular couplers have been designed for systems which require high misalignment tolerance under parking, or for systems that require dynamic movement such as taxi ranks or actually highway movement. They provide reduced sensitivity to varying coupling and improve system efficiency. To understand how we build this, we can take the two single-sided coil topologies which were discussed earlier, the circular and the double D, and place them on a single ferrite structure. So here the circular coil, or we call it here the quadrature or Q coil, is sensitive to vertical fields at the center. However, the double D is sensitive to horizontal fields at the center. So if we take this DDQ secondary and place it over a double D primary, you can see that the double D primary is causing a horizontal field to be captured in the DDQ secondary when it is centered, and that will be picked up by the double D within the DDQ secondary. But under misalignment conditions, this field is now entering the secondary as a vertical field, and that'll be picked up by the Q coil. Another option, which uses less copper, is called the bipolar option. It is essentially two circular coils displaced or overlapped in such a way that they are independent of each other. This enables similar power transfer, and whether it's a DDQ or a bipolar, either coil, circular or double D, or two circulars can be shut down when not needed to maximize the efficiency. To understand how this is done, if we have a controlled current in the primary, then you can have a parallel tuned system which provides a current source from each of the two independent coils into the load. If we tune and rectify these independently, we can shut down either coil at the bridge and then regulate the overall power into the load as required. To understand how this works in practice, we can look at a system which is designed as a DDQ secondary placed on either a circular or double D primary. If I took an equivalent circular on circular system, you can see that the 7 kilowatt power zone as we showed earlier. If I now place the DDQ secondary on this, you can see that the charging zone is increased by a factor of 3. If I took a double D by double D system, then you can see the charging zone here. And if I place the DDQ secondary over top of it, I can widen this by a factor of 3. The DDQ is in fact the same area as the circulars and the double Ds. And this enables us to either have much higher lateral parking tolerance or to minimize power pulsations in dynamic applications. For example, if I was in this driving direction here, I could be picking up power all through this range. Another significant body of literature in the research area is on future road systems. And these systems were interested in putting our wireless power systems in the road for either static, semi-dynamic, or dynamic applications. The challenge of static is we have to do high power transfers for a long period of time in a very thermally constrained environment. Semi-dynamic and dynamic need to take care of movement. The questions in the research literature are around whether we should use lump systems or track-based systems. To give a challenge on this, if we use circular or double D secondaries, it's quite clear that if we use the lump system, either circular and double D in this case, we will get pulsations into the vehicle, pulsations of power with nulls. If we use a multicoil secondary, we can actually have smooth power transfers with minimizing those power pulsations which never go to zero. If we build multicoils in the road, we can actually smooth it even further. And so the question is whether we go for lumped or track-based systems. Excellent piece of work done in reference 34 was looking at all the options available to us. And this has been a topic of discussion throughout the literature. So we can either use single core systems, 2 or 3 phase systems in a linear configuration, or in a meander configuration. The general thrust is that multi-phase systems provide better power and tolerance, but the linear systems are lower cost, and these other systems are typically higher cost, but have higher tolerance and power. As an example of one of these, this shows a system built in our lab. We have double D primaries and we have a multicore secondary, and we're able to operate this system with complete movement. This is replicating a taxi rank system. Part of the other literature is how to sense when the vehicle moves from one coil to another in order to make a decision when to turn on or turn off one of these coils. This can be done using free resonance within the coil which is not on as the vehicle comes near it. And you can see this in operation here. The first coil is on, and in the in-between stage, you can see that as the vehicle moves to an in-between point between the 2 coils, resonance starts to increase within the second pad, and we turn it on, and we support the power transfer into the vehicle from both pads. And at some point, the vehicle shifts away from the first pad and switches off. Overall, we can see that we get continuous power transfer to the vehicle. So in-road research challenges are one of how to ensure compatibility to all the vehicle platforms which will be going into the market. How do we ensure that we meet the various gaps, the power and the tolerance required? How do we design it to ensure that it survives within rigid concrete or flexible asphalt systems, and ensure that it doesn't ask for pulsating power demands from the grid? And of course, it needs to be robust and reliable and won't break down either within the road or cause destruction on the road. If you need any more questions on this, or you want to ask any questions, please be in contact with either Dalipa or myself, and we'd be happy to answer any further questions. You'll also see that I've been talking to a range of references throughout this, and I can just briefly show you these now. Thank you for your attention.